Hey everyone, and welcome to this explainer. Today, we are demystifying a truly massive turning point in the history of technology. For decades, computer processors just kept getting faster and faster, almost like magic. But then, they hit a brick wall. Literally, a physical speed limit. To keep our tech advancing, engineers had to completely rethink how a computer's brain is organized, which gave birth to what we now call multi-core architecture. It is an incredible story about hardware workarounds, the massive software challenges they triggered, and we're going to break the whole thing down for you today.
Okay, let's dive into this. Here is our roadmap. First, the hardware performance wall. Second, the multi-core software challenge. Third, a real-world case study looking at Valve. Fourth, organizing multi-core systems. And finally, the heterogeneous computing future.
Section 1. The hardware performance wall. So, for the longest time, the strategy for making computers faster was actually pretty straightforward. Just crank up the clock frequency and add more complexity to the processor. Engineers were absolute masters at squeezing more work into every single clock cycle.
Just take a look at how this complexity evolved over time. At the top, with the superscalar organization, designers basically started creating longer and longer instruction pipelines. To give you some context, early pipelines had just 3 stages. But Intel's Pentium 4 Prescott core pushed that to 31 stages. Then, they started adding multiple parallel pipelines. But when that hit diminishing returns, just because of the sheer amount of logic needed to manage it all, they shifted to simultaneous multithreading, or SMT, which you see in the middle. That allowed multiple threads to share pipeline resources. But eventually, a single core just couldn't be optimized any further without creating massive design and manufacturing headaches. And that forced the big jump to the bottom layout. Multicore, literally putting multiple independent processor units onto a single piece of silicon.
Now, you might be wondering, why stop optimizing the single core? Well, there's a hard mathematical reason for this hardware wall, and it's captured perfectly by Pollock's rule. You see, you can't just keep cramming more logic transistors into a single core and expect a one-to-one return on speed. If you double the logic in a processor core, you don't get double the speed. You actually only get about 40% more performance. So mathematically, it just stops making efficient sense to build one giant, incredibly complex core.
And this brilliantly illustrates the other huge elephant in the room, heat. To keep driving performance up, engineers were running these complex logic cores at incredibly high clock frequencies, and the power requirements started growing exponentially. Notice just how steep that power density line is for the logic transistors. I mean, they get incredibly hot. But if you look at the memory line right below it, the power density is an order of magnitude lower. So, to keep these chips from literally melting down, designers started devoting up to half of the entire processor chip area to cooler, lower power cache memory, rather than power-hungry logic.
Section 2. The multi-core software challenge. So, the hardware engineers solved their physical limits by slapping multiple cores on a single chip and padding it with cache memory. But here's the catch. By solving their hardware problem, they inadvertently handed a massive, complex puzzle right over to the software engineers, because software wasn't automatically ready to utilize all these new parallel cores.
This raises an incredibly important question, one you've probably asked yourself when shopping for a new laptop. Does having more cores automatically equal more speed? If you upgrade from a quad-core to an 8-core processor, does your software magically run twice as fast? Let's look at the surprising math behind this.
The answer all comes down to Amdahl's law. This principle states that a program's speedup is strictly limited by the portion of its code that absolutely must run in a sequence, one step at a time. So the crucial point is this. Let's say just 10% of a program's code is inherently serial. If you run that program on an 8-core system, you don't get an 8x speedup. No way. You only get a maximum performance gain of 4.7x. That tiny bit of serial code acts as a massive bottleneck for the whole operation.
And honestly, in the real world, it gets even messier. Software doesn't just run perfectly in a vacuum. It incurs overhead. Cores have to communicate, they have to distribute work, and the operating system has to manage cache coherence. Because of all this overhead, notice how those performance lines actually curve downwards as you add more and more processors. It's crazy, but adding more cores can actually make badly written software run slower.
Section 3. Real-world case study with Valve. To really grasp how developers tackled this software challenge, let's ground this in reality. Let's look at a case study from Valve, and specifically, how they reprogrammed their incredibly popular Source game engine, the absolute powerhouse behind games like Half-Life 2, to actually exploit these multi-core chips.
So Valve had to figure out what's called their threading granularity. Basically, how finely should they chop up the game's code? They tested 3 options. First was coarse-grained. where they simply put artificial intelligence on one core and physics on another. But they found this only gave them a measly 1.2x boost in actual gameplay. Next, they tried fine-grained, taking a single task like a data loop and splitting it across many threads. But the timing was wildly unpredictable, and managing that was an absolute nightmare. So, moving past those failures, they hit the nail on the head with their third strategy: hybrid threading.
Here is exactly what that hybrid threading setup looks like for the game's rendering module. Certain systems, like sound mixing, just operate better when permanently locked to a single processor. But scene rendering? That can be spread out. Notice this hierarchical tree structure. Higher-level threads dynamically spawn lower-level threads. They construct scene lists in parallel, and then compute character bone transformations and draw particles across multiple threads simultaneously. They utilized a single writer, multiple readers model, simply because 95% of the time, a thread is just reading from the game's world database, not writing new data to it. It is an incredibly elegant software solution to a very stubborn hardware reality.
Section 4. Organizing multi-core systems. Let's move on and see how this all builds into the physical architecture of the chips themselves. I mean, once software developers actually figure out how to write multi-threaded code, how do hardware designers best lay out those cores and that vital cache memory we talked about earlier?
Tracking the evolution of on-chip memory here is super fascinating. In older multi-core chips like Diagram A, each core just had its own tiny, dedicated L1 cache. But as transistor density allowed for more memory, we evolved through diagrams B and C, eventually arriving at D. This is your modern standard, like the Intel Core i7. Here, you have dedicated L1 and L2 caches for each individual core, but they all share a massive L3 cache. Sharing that highest level cache is brilliant because it reduces data replication. If two cores need the exact same data, it's only stored once. Plus, it allows the chip to dynamically allocate more cache to whichever thread happens to be doing the heaviest lifting at that exact moment.
Section 5. The heterogeneous computing future. Up until now, we've mostly been talking about homogeneous multi-core organization, which just means putting multiple identical cores on a chip. But the quest to optimize silicon real estate, that never ends. To maximize performance and absolutely minimize power consumption, the industry shifted toward the climax of our explainer, heterogeneous multi-core organization.
The biggest trend here is combining completely different types of cores onto the exact same piece of silicon. Specifically, mixing conventional CPUs with graphics processing units, or GPUs. Think of them like a cast of characters with different specialties. A CPU is your speed demon for sequential instructions. Maybe it has 4 cores running at super high frequencies. But a GPU, that has thousands of parallel execution threads. Thanks to programming models like CUDA, we don't just use GPUs for graphics anymore. We harness their massive parallel processing power for general-purpose scientific calculations and heavy data crunching, seamlessly paired with the CPU's sequential speed.
Another absolutely incredible approach to heterogeneous design uses cores that share the same instruction set but vary wildly in power and performance. A prime example is ARM's big.little architecture, which is probably sitting in your smartphone right now. A single chip might have high-performance Cortex-A15 big cores alongside low-power Cortex-A7 little cores. The power-hungry A15 heavy lifters are only woken up for intense tasks like gaming or processing video. But for background processing, playing some music, or just sending a text, the system shifts the workload to the little, battery-saving A7 cores.
Managing this handoff is just a masterclass in operating system engineering. The OS is constantly monitoring your phone's performance needs. Following the performance curve, the software can use dynamic voltage and frequency scaling, literally dialing the voltage up or down to hit specific operating points. If you're browsing on an A7 core and suddenly launch a highly demanding app, the OS models can instantly power on the A15 core, seamlessly hand the application over, and power down the A7. It saves your battery life, and you don't even notice a single hiccup in performance.
So what does this all mean? Well, the journey of the multi-core processor proves that hitting a physical limit isn't the end of innovation. It's really just a pivot point. Hardware engineers bypassed the speed limit by multiplying the cores, which in turn forced software engineers to completely rewrite the rules of programming. But as we look to the future, mixing specialized CPUs, thousands of GPU threads, and low-power cores all onto a single piece of silicon, it leaves us with one fascinating question to ponder. What completely new, unimaginable software paradigms are we going to need next to unlock their true unified potential? Thank you so much for joining me on this explainer, and keep questioning how the technology around you really works.